Elastic potential energy. In this part, we'll talk about the elastic energy stored in a spring. So if we have a spring, we notice that at a certain position, when the spring is compressed or elongated, then if we release it, it will go back to its initial position. This is due to the work of the force, which is the force here is the tension of the spring, T, which is according to Hooke's law equals to K delta L, where delta L is the variation of length of the spring, and this is what we call X. Now, due to this variation, we will have, and due to the work of this force, we will have a storing of energy at a certain position, and this is what we call the elastic potential energy. So this elastic potential energy is given by half kx squared, where you have to pay attention that k is the stiffness of the spring, where x is the variation of length in the spring. So let's say, for example, if this is the spring at its equilibrium position, where if there's no compression nor elongation, then in this case, we say that x is equals to 0. Now, when we compress the spring, so here, the length of the spring, we can name it L0, and this is what we say, it's free length. When we compress the spring at a certain position, so we notice that now there's certain variation. This is the new length of the spring. So there's a certain variation. This variation here, this part here, it's called X. And in this case, it's given by X equal L0 minus L. It's free length minus its length at this position. Now, we can elongate the spring. So if the spring now reaches its maximum elongation, let's pause here. So this means also we have a new length. This is the new length of the spring, and we have a certain variation. Here is the variation, since here is the position equilibrium, right here. So this is the variation, we call it X. Now, in this case, X is equals to, so this is the whole part L, this is L. So we'll get that X is equals to L minus L0. So in all the cases, we can say that X here, X is equal to absolute value of delta L, which is the variation of the length when we have compression or elongation of the spring. Now, let's do a small application. So let us consider a spring with a constant of stiffness K equal 10 Newton per meter and initial length L0. It's extended to 2 centimeters from its position of equilibrium. So we have to calculate the elastic potential energy in the spring. The elastic potential energy is given by half kx squared. We have k is equals to 10, and x is 2 centimeters, so we have to convert it, which is equal to 0.02 meter and square. So we'll get as answer 2 multiplied by 10 to the power negative 3 joules. Let's do another example. What is the constant of stiffness? So K is equal to how much? If the elongation of the spring is 0.15 meter. So here we are given all the elongation, which is X, when 0.72 of any elastic potential energy is stored. So EPE is equals to half kx squared. Here we have 0.72 joules is equals to half, and the stiffness, we have to find it, where x is 0.15 squared. So we'll get that k equal 2 multiplied by 0.72 over 0.15 squared, which will give us 57.6 Newton per meter.